I could have bought you progress in blue stone.
Put some dirt on the
But
side.
it's silver. With some silver lining.
Yes. You should start wearing them to school.
Yes.
And then Thomas Garcia, like when that your mom said you had your John, you said you have to wear them because they must be.
Stop buying $800 pairs of shoes, guys.
That's what we're doing.
That's my takeaway.
Unless they're red bottoms. What kind of shoes are they?
Dirty shoes.
Oh, I know exactly.
Oh, whoa, yeah.
All right.
Actually, maybe you're not
Okay. I think that was everybody. All right. Here we go. Shh. So today I would like to start by continuing on in chapter 8. So we're going to look at section 8.3 today. We're going to look at some specific applications of vectors. So in 8.3, we're going to basically look at two kinds of problems. Okay, they're both kind of story problem. The first type of problem, we have all the tools we need already to handle. The second type of problem, we need a new vector operation to deal with. So we'll be introducing a new vector operation before we do that. But that's the plan for today. Basically just two types of story problems. And I guess we get a new vector operation along the way also. So, our first situation is going to be dealing with these kind of navigation problems. So this problem reads, a boat leaves a port and averages 40 knots. Knots is just nautical miles per hour. Traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? So before we dive into this problem, there's one piece of vocab in here that we probably heard that we're not sure what the heck that means. And it's describing an angle as a bearing. Notice that that's not a standard position angle, that's a bearing. So let's first start by defining what we mean by a bearing and then how to convert a bearing into a standard position angle. Okie dokie. So when I describe a bearing, these are all going to be relative to like the cardinal directions, like the compass rose. So bearings always start at due north and they rotate clockwise. So if we talk about our 215 degree bearing, so that's like 90, 180, and then like 35 more. That gets us our 215 bearing, right? Is everybody okay with that idea? We don't want a bearing, though. What we want is a standard position angle measure. So what I really want is I want this angle. Because then I can just do sine, cosine, tangent to it, just like we did in first semester. No adjustments need to be made. So if I want that angle, I know this piece is 90, that's 90, and then what does this piece in here have to be? Not 35, 55. How did I get 55? 90 minus 35, right? Because there's 90 degrees in the quadrant. You had the right idea. I think you just goofed some mental math, and I know that's rough right after lunch. Oh, I wrote 55. What did I mean to write there? I mean, I wrote 35, meant to write 55. Is everybody okay with that idea? What we mean by a bearing now and how to go back and forth from a bearing to a standard position angle? Okay. So I'm going to just kind of set that aside as a definition that we handled before we started into this problem, because we hadn't talked about what a bearing is before and how to translate that. But that's pretty simple. But if you don't know, what are we going to do with that? All right. So when I read this problem, what I hear is two vectors. Oh, that's not what I wanted it to do. So I hear vector 1. And then I hear vector 2. So I'm going to give these vectors a name. I'm going to call them U and then V. So one leg of my journey is one vector, and the other leg of my journey corresponds to the other vector. And my first goal is going to be to take this information and turn it into a magnitude and a direction for each of these two vectors. All right, so we'll start with the magnitude for U. Remember the magnitude notation that we use the vertical bars around our vector, represents the magnitude of the vector. Everybody's okay? So the magnitude of the vector is going to correspond to the length or the distance that the boat has traveled on that leg. So the first boat goes the boat goes first 40 nautical miles per hour for 2 hours. So how far does it go in that time? 80 nautical miles, right? Is everybody okay with that? Pretty simple. Okay. And then the direction for U, we just did up here, so I'm not going to draw it again. I'm just going to copy down that 235 that we did when we talked about bearings just a moment ago. Does everybody feel okay so far? Now let's do the same thing for vector v. So here we went 55 knots for 3 hours. So that's going to be 165 nautical miles. And our bearing was 162 degrees. Let's kind of figure out our standard position angle from that. So if we go 162 degrees, we go 90, like 72 more. And then I want this spot. So that's 90, 90, 90, and then 18. So my direction for my angle V should be 288. 90 plus 90 plus 90 plus 18. Does that all feel good? Okay. So my next step is going to be to convert my vectors. Well, hold on. My vectors are now represented as magnitudes and directions, right? I've translated the story problem into the easiest vector form I could get. It was ready-made, tailor-made for me to give magnitude and direction. I'm now going to convert from magnitude and direction form into component form. Do we remember the formula to change vectors in magnitude and direction into component form? So the formula is magnitude of cosine of the direction, comma, magnitude times sine of the direction. That's how we convert from magnitude and direction into component form. So it'll be 80 times cosine of 235, comma, 80 times sine 235. Is everybody okay with the formula and how I've plugged the numbers in? So I'm going to go ahead and type this into my calculator to get a decimal. So 80 times, before I do that though, what should I check? The mode of my calculator. Notice that my angles in this problem are being measured in degrees. So if I press the mode button, I want to make sure that the degree mode is active on my calculator. If not, I'm getting all the wrong answers. So if you haven't checked the mode of your calculator recently, I invite you to take out your calculator and double check to make sure you're in degree mode. I think that'll be your most common mode for this chapter. Okay. So now I'm going to just do 80 times cosine 235. And then we'll do 80 times sine 235. So I have like negative 45.9, comma, negative 65.5. We'll do the same thing now for vector v. Bless you. Golly, that's a lot of bless yous. You're welcome. You got the allergies?
Yeah, I think so. I think I've had them all my life.
It's probably the math.
Oh, yeah.
So again, I just went ahead and plugged this into the formula, same way as we did before. And then into my calculator it'll go. So I have let's call it 51.0 and then negative 156.9. Everybody so far so good. Now let's think about what's happening in actuality with our boat here. So if this is like the port, we're going like negative 45.9 over and then like negative 65.5 down. That's the first leg of our journey. That's vector u. And then we're going 51.0 over and negative 156.9 down. That's like the second leg of my journey. That's like my v. And what we're looking for then is the magnitude and direction of this vector. I'm going to call it r for resultant. And this is the guy we want to know about. Does that all feel okay there? So what vector operation did I just draw when I draw those vectors head to tail like that? I'm drawing vector addition. Vector addition. So what we're saying then is that r is just vector u plus vector v. This is why I went through the trouble of writing those vectors into component form. I think that's what I wrote, yeah. So there's my addition problem. How do we do vector addition again? We add the x components, and then we add the y components. That's it. Easy as that. So I took my 45.9, or negative 45.9, and add my negative 65.5. So I get... Oh, that wasn't what I wanted to add. Oh, dear goodness. Now I really made a monkey of it. All right, we had 80 cosine 235 plus 165 cosine 288 is what I really meant to add. There we go. And then I had 80 sine 235 plus 165 sine 288. So that. Yes. Sure. If I look at this point, does this point seem like it's 5.1 comma negative 222.5? That seem about right? Yeah, that looks about right. So I feel good about what's going on, right? My numerical answer matches the picture I've drawn, or seems to confirm that, so I like where I'm at. So far, so good. Now that I have R to find how far the boat is from port, I just need to find the magnitude of R. To find the magnitude of a component form vector, it's just going to be the square root of the x component squared plus the y component squared. So again, I'll just bust out my calculator here to do that. And I get another 222.5, which is hopefully not too not very not so surprising, right? Most of the distance we're traveling in our resultant vector is in that y direction, right? The x is contributing very little. It's a very small number relative to the magnitude of the y direction. Does everyone feel okay there? So that's the distance. Now to get the bearing, we have this guy right here. We want that angle. So to do that, we're going to define, let me pick a better color. We're going to define this angle between the terminal side of our angle and the x-axis as alpha. And I know that the whole circle is 360. So my direction should be 360 minus that little alpha. Mm-hmm. Is that okay there? And that alpha we always find the same way. It's going to be tan inverse absolute value of the y coordinate over the x coordinate. And now it's just calculator time. So I'll do 360 and then minus tan inverse, and then to get the absolute value here, I'm going to do math. I'll go over to the number and pick absolute value. And I'll do y divided by x. Close my parenthesis and then press enter. And I get about 271.3. Which again, if I look at my picture, that should make sense, right? That little sliver right there, is that about 1.3 degrees? Yeah, probably. Like it's not very much. That's for darn sure. So that seems to, again, confirm what I've drawn, which I like to see happen, right? I'm hoping that my picture and my numbers match. If they seem to reinforce each other, what's going on, I should feel pretty good about my process. Questions on what I've done so far?
absolute values?
On your calculator?
Yeah.
If you press the math button, and then you go over to the number menu, ABS is short for absolute value. And it's all you need right there. Cool? You found it? Okay, perfect. All right. So the second type of problem, we're going to need to define a new vector operation to do this called a projection. So here's the idea. I'm going to draw a picture before I kind of explain what's going on because I think the visual makes a big difference here. So let's say we have some vector u, and I want to give it maybe a little bit more space there. And then I have some other vector v. Notice that I've put them so that they are both starting at their tail is in the same location. And what I want to do is I want to rewrite my vector u as the sum of two vectors, one of which is in the same direction as v. So basically what we're going to be doing geometrically is I'm going to have something like that. So the name we give this yellow vector, we're going to call this the projection onto v of vector u. Bless you. And then the name I typically give this other one is I just call it W. So it's basically, you know how like we can say, okay, say like we have the number 5. I can take that number 5 and write it as, say, like 4 plus something, right? Like 5 is 4 plus 1. This is the same idea here. I'm taking my vector u and rewriting it as the projection of vector u onto v plus this other thing w. It's the same idea. I'm just breaking my vector into the sum of two vectors. The catch is that this projection vector is in the same direction as some other specified vector, right? If you look at the picture, obviously the yellow vector is the same direction as the green or the blue vector, right? Everybody can see that? So the question then becomes, how do I compute that projection? Right? How do I actually compute that? How do I get given a vector u and v, how do I find that projection? Well, this is the formula we're going to use. So for non-zero vectors u and v, the projection of u onto v is equal to the dot product of u and v divided by the magnitude of v squared times the vector v. So as a reminder, when I do the dot product of two vectors, I just get a number back, right? It's just like a whole number, like a regular old number, right? When I do the magnitude of a vector, I just get a regular old number, right? So this u dot v over magnitude of v squared is just some scalar quantity. It's just a number. All this is a fancy scalar multiplication. Everybody's okay with that? Now, if we go back to our picture above, I drew v like super long, right? Everybody's okay with that? Now, when we go to these application problems, sometimes the vector you're going to be projecting onto, you'll be given, like it'll be specified the magnitude for that vector in the problem. But it won't always. When it's not, we have the freedom to choose the magnitude for that vector v. What do you suppose will be the magnitude we choose if given that option? Pick 1. We want to choose vector v to be a unit vector in general if we have that choice. Sometimes we don't, but sometimes we do. Okay? So let me just kind of drop in those 2 notes here. Oops. Okay, note 1 is just kind of saying that if we're not given enough information to find the magnitude of vector v, we're just going to assume that it's 1. The vector v is a unit vector. And then the second note is just saying that that coefficient, that u dot v over magnitude of v squared, is just a scalar quantity. So we're just really talking about a scalar multiplication problem here. All right, let's do some examples of computing this vector projection. So our example says, find the projection of u onto v, then express vector u as the sum of 2 orthogonal vectors, one of which is the projection. When we say orthogonal, what do we mean if 2 vectors are orthogonal? That just means that they meet at a 90-degree angle, which is exactly how we drew this picture up here. So really the second part of this problem just asks us to write this statement, basically. So let's find the projection first, and then we'll worry about that second part afterwards. But that's really all it's asking for. So the projection of u onto v is going to be u dot v over the magnitude of v squared times vector v. And now I'm just going to recopy the formula, but I'm going to put in my values for vectors u and v. Everybody's good with what I did there? Basically just wrote the numbers in their spots. Now, first thing I'm going to do is go ahead and do this dot product. How do I do the dot product of two vectors? It's the product of the y components plus the product of the, the product of the x components plus the product of the y components. So that's going to be 3 times 6 plus 1 times negative 4. Everybody okay with that dot product formula? Next, I noticed that, hey, when I plug this stuff into the magnitude, that square is going to cancel the square root. So I'm just going to be left with like 36 plus 16. So far, so good. Three times 6 is 18. 1 times negative 4 is negative 4. 18 plus negative 4 is 14. 36 plus 16 is 52. Everybody's okay there? I notice that 14 over 52 is a fraction that I can reduce. So I'll write that as 7 over 26. Then I'll go ahead and do that scalar multiplication. And once again, I see that I can reduce Now, I showed a ton of steps here to do the computation. If you're comfortable doing less steps, feel free to do that. I showed like a lot of work there. I didn't want to let anybody or lose anybody. I haven't been here in a couple of days. I don't really know how comfortable you are with like all these vector operations. So I'm using this also as like an opportunity to review like how we do these individual vector operations that are part of this larger problem. But it's not unreasonable that you're able to do like dot products and stuff in your head if you need to, or do it in a single step if you'd like. That's no big deal. I'm just trying to write it out for your notes. So if you're going back to look at something, like it feels like a pretty complete record of what we're doing. Okay, so that's the first piece, finding the projection. The next thing is it wants us to write our vector u as the sum of two orthogonal vectors. So we're going to do this. We're told that u is 3, 1. We know our projection is 21 over 13, comma, negative 14 over 13. And we're going to use that then to find w. If I want to get w by itself, what do I need to do to both sides of this equation? I just need to subtract this projection vector from both sides of my equation. Does everybody feel okay there? To subtract two vectors, I just subtract the x components, and then I subtract the y components. To do that subtraction, though, I need to have a common denominator. That common denominator is going to be 13. So really, I'm going to think about that first vector as 39 over 13, comma 13 over 13. So my W should be 18 over 13, comma 25 over 13. That should be 27. I don't know how I managed to. 3 plus 4 is definitely 5, right? Yay. So if I look now, I needed U, the projection of V onto U, and then W. Well, I have U, I have the projection, and now I have W. So I have now everything I need to rewrite U as the sum of orthogonal vectors, one of which is the projection. Brody? It's a typo. Yeah, should have been 13 the whole way. It was up here. I just goofered. Thank you for pointing that out. Saw you making faces back there. I was waiting for the question, so I'm glad you asked. Again, if you think I've made a typo or a mistake, please speak up. It happens from time to time. Nobody's perfect. Maybe tomorrow. Get there someday. All right. Does that feel okay on how to do this projection calculation? Okay. So the type of application problem that involves this are going to be like these force problems. So I have two examples to do of this, because there's actually a shortcut for one of them that I want to point out. And then one where the shortcut is unavailable to do, so I want to point out the difference. This problem says Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill. So oftentimes in physics, when we're dealing with like the application of forces, these vector projections become a very natural tool to use. So when I'm reading one of these problems, I'm looking to identify the vectors involved in the problem. So I'm going to have my force vectors, and then I'm going to have like a direction vector. Okay? So in this problem, if we think about you're sitting at the top of a hill, and if you slide down, what is the force that makes you slide down, that causes you to move down the hill? Gravity. So that's going to be one of our forces. I'm going to call that G. What is the magnitude of G going to be in this problem? 165 pounds. What is causing things to have weight? Gravity, right? Because if you go out into space, what happens? You're weightless, right? Because gravity is no longer acting on you because you're no longer on, like in a curved, wow, it's getting beyond this. Because you're off the planet, right? The planet's what's causing the gravity. You get too far away from it, you get outside the gravity. Okay? Now, what direction does gravity pull us? Down. So our gravity vector is just pointing straight down, right? So what's the direction for gravity going to be? What is that angle? In degrees, though, standard position angle. 270. Everybody's okay with that? Just 90 plus 90 plus 90? And now I'm going to resolve my vector G into component form. So that comes out to be 0, negative 165. Which probably after you drew the picture of our vector and thought about it for a minute, went, no doy, that was going to be the component form for it. Look, the vector's pointing straight down, and its magnitude is 165. And it's just negative 165 down. Oh yeah, of course. I didn't want to go with the intuitive shortcut before we showed you the full way of doing it. I don't like doing shortcuts before the full explanation, right? Is everybody okay with that? So the problem now is asking how much of this force is directed down the ramp. So the ramp is going to be the hill. So I'll use H for my other vector. Now, the hill is not a force, right? Do we know anything about how long the hill is, or its magnitude, what its magnitude should be? Given any information as to what that is in the problem? Well, that's the direction, because it's in degrees, right? Or has to do with the direction. But are we given anything about how long the hill is, or what its magnitude should be? Given nothing about that, right? Guess what we do? As we mentioned before, we're going to assume then that the hill is a unit vector. Its magnitude is 1. Everybody's okay with that? Okay. So if I draw my hill vector, we're going downhill. So we're doing like one of these guys, right? Now it tells us the angle of incline is 25 degrees. So like that's 25 then, right? Everybody's okay with that idea? Which means that that angle is also 25 degrees, right? From geometry, alternate interior angles. Take my word for it. So my direction for my hill vector is going to be 360 minus 25, or 335. Does that look okay so far? So if I write this in component form, and I go to my calculator, say 0.91 comma negative 4.22. So far, so good. And now the answer to my question, what I need to find to answer how much of that force or what amount of force is sliding down the hill, is I need the magnitude, let's just say F, is equal to the magnitude of the gravity vector projected onto the hill vector. So far, so good? Okay. So if I start plugging things into my formula, that's my projection formula. And now I'm going to plug in my values for G and H. But where it says the magnitude of H squared, or where it says the magnitude of H, I'm just going to write 1. How do I know that? How do I know the magnitude of H is just 1 in this problem? We chose it in the beginning, remember? Oh, yeah. Now, if I plugged in the numbers and did like the square root of blah, 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 you know, like I did the whole thing, I'd still get 1. I did the magnitude formula there, but like, my life's hard enough. I know what it is. Let me just write the number in. save myself the problem. All right, so let's go ahead and do that dot product. So I'm going to have 0 times 0.91, and well, that's just 0. And then negative 165 times negative 4.2 is going to be, grab that answer. So 69.73. Everybody's okay with this so far? So a helpful identity or helpful rule here for these kinds of problems is if I want to do the magnitude of a scalar times a vector, that's just going to be the absolute value of the scalar times the magnitude of the vector. They can kind of pull that scalar out front and separate it. And remember, this vector is vector h, right? What's the magnitude of h? 1! So this just simplifies down to 69.73 pounds. So our shortcut here is this. Anthony, what's up? So this is our shortcut. That if the vector we're projecting onto has magnitude 1, it's a unit vector, then to find the magnitude of the projection vector, I can just do the absolute value of the dot product. Which was what we found right here, almost immediately, right? It's one of the easiest parts of our computation. Again, to be able to do that, though, the magnitude of that vector you're projecting onto must be 1, or else you got to do the whole shebang-a-rooney again. All right, let me do one more example and we'll be done for today. Example 13. This says a crate is being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assuming the crate is of negligible weight, what is the amount of force directed up the ramp? First question, is there gravity involved in this problem? Do I have a gravity vector? The answer is no. Why not? What part of this problem tells me that gravity is not a factor in this problem? Exactly right. If the crate has no weight, then there's nothing for gravity to act on, right? Everybody's okay there? So what I have is I have this pull vector and I have a ramp vector. I have the force from the person pulling the crate, and then I have it being directed onto the ramp. Is everybody okay with that? If I also had a weight attached to the crate, I'd have a third vector. I'd have P, G, and R. And before I proceeded to do the projection, I'd have to add P and G together and then take that resultant vector and project onto R. If you have a situation with 3 vectors, I think that does pop up in some of the homeworks. But you just have an additional step at the beginning where you have to add the 2 force vectors together. Okay. For our pull vector, what's the magnitude going to be? $100. Yeah. And the direction then, if I draw my picture, that's basically what's happening, right? So my standard position angle is just 40 degrees. Notice this is different than the previous problem because here my vector's in the first quadrant as opposed to the fourth quadrant. Because we're being pulling up, right? So the force is going in like that direction. You guys kind of see that? So my pull vector is going to be 100 cosine 40 degrees, comma 100 sine 40 degrees. So 76.6 and then 64.3. So far, so good. Now let's look at what we know about the ramp. We're told the ramp measures 4 feet horizontally and 2 feet vertically, right? Or sorry, 10 feet horizontally and 2 feet vertically. So it's like that. Now, we're not given anything as a magnitude or direction, but that's, yes, sure. But that's okay. In fact, we're given something better. Guess what the component form is going to be? If we go 10 over and 2 up, just the component form for r. That's even better than getting magnitude and direction, right? Nice. Unfortunately, what do I notice about the magnitude of r? It ain't 1. Should be able to look at that and see that immediately. That's a bummer, but at least I didn't have to do much to get it. So then I need to do the absolute value, or I'm sorry, the magnitude of the projection of P onto R. It's the magnitude of P dot R over the magnitude of R squared times R. So again, I'm just restating the formula. Let's fill the things in. So P is that. R is that. Oops. The magnitude of R is that, and it's squared. And then times R. So let's do the dot product. So that's the product of the x's times the product of the y's. So 10 times 76.6 plus 2 times 64.3. So I have 894.6. And I know the squared is going to cancel the square root down here. So I just have 104. Actually, let's... So save myself a little work. I know what the magnitude of this is, right? That it's just the square root of 104. Because I know that I already did it down here. Is everybody okay there? So now it's just going to go to my calculator. So the absolute value of 894.6 over 104, well, I don't need, an absolute value to do that. They're both positive numbers. So I get 87.7, and that's my answer. Is that okay? What we did? Okay. Other things to be on the lookout this week. The plan. We will do our homework quiz at some point this week. That homework quiz would be covering sections 8.1 and 8.2. So nothing of what we did today. Just your basic transforming vectors between the different forms and doing vector operations. They're unannounced. So, okay. We'll plan on a day this week to do Some more practice on 8.1 and 8.2. That'll be our Delta Math assignment. And then we'll cover section 8.4. That'll be the last section in chapter 8 that you guys are going to be responsible for. So chapter 8, 5, 8, 6, 8, 7, none of that we're doing. They're all the three-dimensional pieces. You guys are not responsible for that. So that'll be the end of the stuff by Friday this week. We'll finish up the content for chapter 8. So the following week we'll plan on a review day and then the chapter 8 test. So that'll be coming the week after. Okay with you guys? Homework quiz this week, test next week. What? Homework quiz this week, test next week, basically. One last thing, your assignment. From this section is going to be 41 through 50. Last class, we would have assigned 15 through 40. All of those together are going to be part of PS2, problem set 2. So again, everything that we assign, that has at least a class day after it gets in that weekly problem set. So it's not uncommon to have like a long one and a short one on the days where we have a 3-day week or 3-class week and a 2-class week. Just kind of how the pattern goes. Every once in a while you catch a day with no problems or a week with no problem set. Where you run into the chapter test or something and you didn't have anything else going on that week. That happens. Or you get a snow day or something, Is everybody cool as to what the rest of the week looks like or what the upcoming schedule is going to look like? Again, that homework quiz looking at sections 8.1 and 8.2. So just changing your forms of vectors and doing vector operations. No application. Can you add, scalar multiply, find magnitudes and directions? Can you take a magnitude and direction, turn it into component form, that kind of stuff. Like all the little sub-steps that we did today in class. If you felt okay on those, should be a breeze. Very computational, nothing tricky going on there. I'll be sometime this week. We'll have a Delta Math as a helpful review for some of that stuff. And then we'll finish up the chapter with 8.4. So far this has been okay, what we've been doing. I know today was hard. Yeah, today's probably the hardest section in chapter 8. But the first two, if you're okay with the notation, the vocabulary, like the actual computations of these things is really simple. You just have to remember what to do. But like the how to do it is easy. What you have to do, remembering the names and the formulas and stuff can be, a lot at first, but after you've done some, enough of them that they stick pretty good because they're pretty different.